Dynamic reduction methods are needed in finite element analysis because the model that has been constructed often is too large and complex to efficiently solve for the vibration characteristics. For instance, an automobile might have 1 million or 2 million degrees of freedom, mostly caused by the need to model the geometry of the problem. Not so much stiffness or mass distribution, but just to get all the angles and holes and corners and brackets and so on. Therefore, there's some need to simplify in a consistent way the scope of the problem so that a person can understand the lower modes of vibration of the system. It's been my experience that in stress analysis, in static problems, often the interest of the designer, engineer, analyst is to find details around local portions of the structure. Where does it break? Where does it fatigue? And those are local ideas. In contrast, the dynamicist wants to get global behavior. What are the long wavelength frequencies that are involved? So it's interesting. It's almost a conflict in function between the static stress analyst and then the dynamic analyst. Well, dynamic reduction methods are meant to bridge that gap. One of them is really straightforward and easy to discuss, and that's the so-called static condensation. Now, this is a nodal condensation as opposed to a mode condensation that we studied earlier under the modal solution methods. So the concentration is how you handle the degrees of freedom at nodes in this case. Unfortunately, to move beyond static condensation gets tough very quickly. I find it more difficult to teach that material, and so I don't stress it as much. I view it as an advanced topic. When you get into component mode synthesis, generalized dynamic reduction, some of those methods are really fairly theoretically involved. So what I'll do is pull my punches a little here and hit static condensation pretty hard, and then kind of wave my arms a little on the more complicated reduction methods. Now, this is okay. I'm going to argue it's okay because some of the new solvers don't really need this simplification. For instance, the Lanchos method seems to work for fairly large problems in a direct way. And so I hope that the user can figure out in your own corporate setting of what sort of dynamic reduction methods you're interested in. There are a lot of vehicle people that still really like component mode synthesis, and that's a super element type of condensation approach. Well, the procedure will be to talk in general about dynamic reduction, hit the static condensation rather hard on Gyan Reduction and do some examples. And then I'll just wave my arms at generalized dynamic reduction and component mode synthesis. We'll follow with some problem session examples, which are primarily the static reduction type up here. I'll start off with a bit of an overview of dynamic reduction. In dynamic analysis, the necessary steps are to assemble the equations, solve them, and then recover the forces and stresses that are the internal field variables in the problem. An optional step, though, which is so important, is this one, where you might reduce the number of degrees of freedom in the system. Basically, you pass from a set of physical degrees of freedom to a set of coordinates that are more or less artificial. Sometimes that reduced set of coordinates carries within it the more complicated behavior of the whole system, but in some idealized way. If you don't do dynamic reduction, you'll find that the solution of the equations here really becomes the expensive part by far, more than 90% in most cases. So you would be willing to do a certain amount of work at this stage in dynamic reduction in order to reduce the solution cost. There are several forms for dynamic reduction. We've already spoken about a modal approach using normal modes as our building blocks. Then the nodal condensations are such as the Guyan Reduction here. Generalized Dynamic Reduction is a bit in between where you have somewhat of a global and somewhat of a local view on the situation, and we'll show some of those equations later. Component mode synthesis is the dynamic version of superelement theory, where you segment your larger structure into pieces. Then those pieces are joined after they're separately analyzed dynamically. And one key question there is, how do you join them together? Certainly if you use a modal solution alone for really large problems, you may get into troubles with the cost of eigenvalue extraction. And then as you get above 10,000 degrees of freedom, you're really forced to go to something pretty powerful, perhaps component mode synthesis or these newer Lanczos solvers. The Lanczos solver has pretty well swept through the industry as I speak and is now the dominant large problem solver. Now let's discuss this Gyan reduction or static condensation and see how it works. We can follow it rather well. In fact, you should understand this method cold. I think it's useful because it also gives you the whole spirit of other condensation methods. We'll illustrate this with the MSc NASTRAN data definitions and their sets of variables. The original set of physical variables would be called U sub g, and then after reducing out the multipoint constraints, you're left with a set U sub n. At that point, you apply the single point constraints, and you're left with these degrees of freedom U sub f. Here's where condensation enters, and there are a certain number of degrees of freedom that are considered to be omitted degrees of freedom. When those are taken out, you're then left with the analysis set of degrees of freedom. Even the analysis set, which is what we will work with today, can be subdivided into those degrees of freedom that represent rigid body modes and those that are or need to be constrained if you wish to remove them, and those that are the final independent degrees of freedom, which are, you can think of as the leftover degrees of freedom. But basically in dynamics, there's no need, as there is in statics, however, to remove rigid body modes. So it's better to work at this analysis set of variable level here. So we will be looking at Gland reduction in the way that you progress from this set of degrees of freedom here, and how you break that into this set and this set. We won't go to the finest, smallest detail where you're worried about degrees of freedom that characterize rigid body modes, since in dynamics they can be carried along anyway. Let's work out the mathematics for the Gyan reduction, and we'll do it, as I'd mentioned, in terms of those sets of variables subscripted with F. We might call those free degrees of freedom, just to coin a word to let us discuss what that is. And the A set will be the analysis set. So if we write the equations of motion at this stage, then the multipoint constraints have been reduced out of the system and the single point constraints have been reduced out. So these then are the free degrees of freedom that describe the active degrees of freedom that remain. At that stage there would be mass terms and damping terms and stiffness terms. These are pretty close to physical degrees of freedom at this point, with some agglomeration effects into the reduced matrices at this level, but closer to a physical set of degrees of freedom. But now we want to make a strong distinction between the original physical degrees of freedom and then a reduced analysis set by doing this kind of partitioning, where we partition these free degrees of freedom into the analysis and the omitted set. Now I'm going to do poetic license here, or author's license, to assume that those were numbered in a way such that I can consecutively partition out these omitted ones. Now normally the analysis set ought to be less in the ratio of 1 to 10, let's say. You'd like to reduce your degrees of freedom greatly by doing this method. So I don't mean that these two vector subcomponents here are of the same size. One of them, the omitted set, is generally way bigger than the other. Now, what we're going to assume is that the relation between the analysis and the omitted variables is based on static equilibrium concepts. That makes this sort of a first-order correction for dynamic condensation. And other people will come along later and say, hey, I can improve this by 5–10% by accounting for those degrees of freedom that are omitted in a dynamic way. But we don't do this. You need to walk before you can run in this case. So you actually do a mental experiment, really starting here, and I'll draw an arrow here for a short time, and then I'll tell you when we stop doing this. We drop out the inertia and damping forces and look at a static problem, which means that you're looking at your dynamic problem in a quasi-static way, as if dynamics really didn't matter, and all of the degrees of freedom are related purely by the springs that connect them, the elastic forces. Let's carry out a mental experiment now to help us eliminate the unwanted degrees of freedom in this problem. One way to do it is imagine a simplified structure such as this beam-like structure shown here, and identify certain important degrees of freedom such as these analysis degrees of freedom at the right end, the center, and the left end. And then identify less important degrees of freedom, such as these at the intermediate spots there and there. Then the analysis nodes are to be treated as master nodes that control the whole system. This reminds me of the lofting curves that were used when I worked years ago at Vought Aircraft and at Boeing, where they had long plastic strips, and then these strips were held in place at intervals by what they called ducts. And these were heavy lead bodies that had a nose on them, and they looked a little bit like a duck. That's where the name came from. That fit into the slot along the top edge of this plastic strip. And then by controlling the shape of that long strip at intervals, the draftsman had a nice smooth contour to follow with their pen. And this is very much the same philosophy that we have here. We want the analysis degrees of freedom to control all of the shape of the body statically. When we write out the equations, presuming that the analysis degrees of freedom are above the partitioning marks here and the omitted degrees of freedom are below, then we have this set of equations. For this mental experiment only, we don't put live loads on the omitted degrees of freedom. Many students who study this forget later on and think that you can't have live loads on the full structure's omitted degrees of freedom. That's not true. Now these are the physical degrees of freedom presently, and these are physical forces on the analysis degrees of freedom up above. You're able to partition out and solve the second large set of equations here, which involve these coefficients shown below. The KOA matrix, which is rectangular, the KOO matrix, which is square. Then by inverting the KOO matrix, you can solve for the omitted degrees of freedom in terms of the analysis degrees of freedom. So this is a mapping that you might want to consider moving in this direction. And very effective then at letting these analysis degrees of freedom control the omitted degrees of freedom. We'll give that mapping matrix a symbol G, and here it is. And we will include the minus sign within that definition shown here. I suppose G can, as a crutch, can be thought of as a Guyan transformation here. So then you have the ability to take the smaller set of variables U sub A and let it drive the larger set U sub F over here. Interestingly, to expand this set in the static way we've had just described, then you use the identity matrix here to map into the smaller set, say of relative size 1, and then you use the GOA matrix to give you the omitted coordinates here. So it's as if there's two parallel pipelines here going from right to left. The analysis degrees of freedom propagate straight through this system into the free degrees of freedom, and the omitted ones have to be mapped to become their rightful spot in the free degrees of freedom. All right, so we've got a mapping, we've got a way to statically condense this problem. At this point we have ended the mental experiment, which was up above, and now we get back to the real world. We look at the full equation of motion for our free degrees of freedom, and we replace the free degrees of freedom with the equivalent mapping version. Now, if we want to take a single derivative of this, that works. You can take a second derivative, that works. So I can map not only the displacement field, but the velocity field and the acceleration field with the same mapping. That's because all of these quantities in here are not time dependent. That was from our static experiment, a static curve. And then on the right we will also consider that the original forces on the system here were, and these are close to physical forces here, are an F bar of A and an F0. I carry the bar temporarily to avoid the use of the F sub A, which I'll have later on. So I'm reserving the unbarred symbol F for later final use. All right, we are in the same position as we've been earlier in this lecture series, where we have, say, n equations in m unknowns, and we need to do something to convert this into a better handled set of equations. And again, we look toward an energy approach where we can pre-multiply by something that's displacement-like. This particular set of equations here would, in a plate structure, have alternate translations and rotations, and it's numerically not real well posed at this time, and so we'll move to the next figure to show the Galerkin type approach. Our set of equations then is a set of force and moment balances at this point, but if we do a pre-multiplication with a displacement-like vector, then we're going to end up with an energy balance instead. So we pre-multiply by our same transformation matrix, and that gives us this set of quantities, and we get a new kind of mass here out of this triple matrix product. And we'll call these the analysis mass terms. Here we get a new kind of damping matrix that we'll call the analysis or reduced damping terms. And here's a new kind of stiffness shown here. On the force side, we get a new set of equivalent loads. These are A set loads. These are have become more and more artificial. They're not the original physical set of loads on A, but they're the representation of all the loads in the system and how you have to agglomerate those at the remaining few degrees of freedom. So these are basically equivalent forces over here. In the earlier terminology where we had dealt with modal degrees of freedom and generalized degrees of freedom, we got generalized forces. And this is definitely that same philosophy. You might think of these as reduced degrees of freedom and reduced The theory for gland reduction is really rather nice and can be incorporated into computer codes rather straightforwardly. There's a few decisions to be made. I'll show how those have been resolved in the user implementation in MSc NASTRAN. Here you have a body that is a potato shape and has live loads in various places on the body, some on what are soon to be analysis degrees of freedom and some on what will be omitted degrees of freedom. How should you model such a system as this? Well, for one thing, you should take any point or any area here that has a large mass and make sure it has analysis degrees of freedom describing it. That way you're not using the so-called beaming out of the mass effects there to some other node point. So it reduces the effect of the static reduction. You should distribute the A points over the body somewhat uniformly so that you're doing a fair job of representing the total geometry. That also means that you don't have to beam out the inertia effects so far and the damping effects. Now these two are rather common sense. The third one is not so intuitive, and that's the feeling that it's better for the A set to have both the translational and rotational set of degrees of freedom. And that means you're going to do this breaking down of degrees of freedom into analysis and omitted degrees of freedom node by node. That's not obvious. I did a problem years ago with a woman professor from China, Mrs. Zhu, and we decided at that time to include only translational degrees of freedom in the analysis set. The rationale was okay there because it was a civil engineering structure and it was going to be easier to measure translational accelerations at points and not have transducers that measured rotational effects. I think by now there are probably good transducers for both, but it was somewhat experimentally motivated to not do this third user-friendly action. As a result of this third one, though, it's relatively easy to set up runs in MSc NASTRAN because you only need to mention the analysis nodes and then proceed. Notice that you'd rather call out the analysis nodes than the omitted nodes because they are perhaps 10 or 100 times as numerous. So that's the convention in typical problems run on MSc NASTRAN. My teaching style in the past has typically been to try to break down a larger finite element process into a simple hand calculation aside from the use of the computer. This helps develop intuition, and it can be done, luckily, for Gyan Reduction here. A physical problem that I will take is going to be trivial then because it's a simple beam element and a single one undergoing small amplitude vibration in the XY plane. The idea is to find the fundamental flexural frequency in the XY plane, ignoring the axial, torsional, and out-of-plane vibrations. Again, we're going to have a compact cross-section, say a rectangular cross-section. So if these are principal coordinate directions for principal axes of inertia, then the problem uncouples nicely and we can just study flexural vibration in the XY plane. Physical modeling is to use the conventional Euler-Bernoulli beam theory so that plane sections remain plane, and we constrain those out of plane motions and the axial and torsional motions. Boundary conditions at the root are that there are no rotations nor translations there. At the free tip, you find that you have no moment and no shear. In the finite element modeling, I'm going to first take the most odious comparison that I can by constraining the tip translation to be the omitted degree of freedom and then using the tip rotation to be the analysis degree of freedom. Now, that means that we are trying to make the rotation at the tip control the entire dynamics of the problem. Furthermore, if I use the lumped mass approach, that means I'm concentrating all the mass at the tip as a point mass, and there's no rotatory inertia involved. Somehow this condensation method has got to account for that and convert that translational inertia effect into something governed by the rotational degree of freedom. So that's really not easy. Now it will turn out that this works, although we have some 20% error in this case. So when I pushed the problem this hard, I thought maybe I won't get answers that make any sense at all. Here's the degrees of freedom that are shown. Of course, we're constraining the tip with these degrees of freedom. So the only free degrees of freedom are those two here. And I'm going to make the U3 be the omitted degree of freedom, and in other words, a slave to the U4 degree of freedom. So this is the toughest case possible, particularly when shown below that I have a point mass out at the tip when I use the lumped mass matrix. Remember that it moves half the mass to the tip and half to the root. Well, the root mass is disabled and doesn't even move then. By moving half the mass to the tip, we're somewhat overemphasizing the inertia effect by moving it outboard, but then we're requiring that that be governed by the static motion of the rotation of the tip. So right off the bat, you might say you've lost the entire inertial effect, but you haven't, because in the static relation that Guyan has developed, if there is a tip rotation, there will have to be correspondingly a static tip deflection. And that was the whole idea of that approach. Now dynamically they may not be related, but statically, as soon as I give a positive angle here, this beam will naturally go upward. So the inertial effect is properly accounted for. Now let's go to the solution. We'll gather the equations of motion for all of those original degrees of freedom. This would be called the G set of degrees of freedom because we are just now applying the single point constraints at the wall. Those cause these first degrees of freedom to be 0. When we partition those out, then we really are going from the G set now down to what we've called the F set of degrees of freedom. We haven't yet done the condensation. We're left with these reduced matrices here, which are still physical terms as they stand. Now we want to do the condensation approach. Our lumped mass matrix effectively moves half of the translational mass out to the free tip and half of it to the root, where it's constrained anyway. Here's the mass matrix reduced to the free coordinates, and here you see the tip mass of 1/2 the total beam mass. Stiffness comes from the Euler-Bernoulli theory, simple beam theory. We now do our mental experiment, which is a static problem. So right here we draw a line and say we're going to do this mental experiment. We don't allow forces on the omitted degree of freedom, which is translational, but we do allow a moment here on the analysis degree of freedom. Then we use the first equation in this case to solve for the translation in terms of the tip rotation. Because the beam moves from 0 slope at the root to a tip rotation out here, you might say that this makes sense because the tip deflection is taken to be the L/2 times the tip rotation. And if the average rotation over the length of the beam is half of the tip rotation, which would be approximate, then you're getting a displacement by measuring an angle through a distance. So it's pretty close to the normal definition of arc lengths and so on. So you can get some physical feeling for this expression, so it's not completely stupid. Now let's form our coordinate transformation. And the analysis degree of freedom U4, which is a rotation, maps directly into U4, which shouldn't surprise us. And then it also creates the translation here by this factor L over 2. Now, that's the end of our mental experiment, and now we progress to the real problem again. The real problem that we're interested in is not forced motion, but finding the natural frequency of this system, the lowest natural frequency. So we put zeros on the right-hand side. There are no live loads. Then we've got our various matrices here, and we've got our transformed variable here. So we're down to the analysis set. We pre-multiply by the transpose of that coordinate transformation here to put this on more of an energy basis. So we collect terms and simplify them and get the resulting differential equation for free vibration. Here's the equation, and you have a generalized mass term and a generalized stiffness term. Now, from here down to the actual answer, it's just a matter of putting in the harmonic motion, realizing that derivatives bring out minus omega squared. Collect terms. You have all of these terms that multiply a term here, which is an amplitude term. Solve for the unusual situation where you can have an arbitrary amplitude, and it occurs when this coefficient here is 0. So you can have equilibrium with any amplitude at this specific frequency. Sometimes you might plot a curve of frequency over here versus this amplitude U4 here, and you find that there's a point in along here at a certain frequency, and that's what we've just found, which is a so-called natural frequency. Here is the resulting number, and when you compare this with the classical solution, which has a constant out front of 3.52 rather than this 2.82, you find our solution is low by 20%. At first you say, wait a minute, you're never supposed to be low on these approximate solutions if you're truly within the Rayleigh-Ritz or the potential energy format. But in this case, our lumped mass approximation is a non-physical approximation, and it has moved so much mass out to the tip that it has lowered the frequency in this way, and so it is explainable. Generalized Dynamic Reduction was developed by Richard McNeil some years ago, and it's been very powerful, used by a lot of vehicle companies for studying large problems. It's a combination of two methods of a Guyan type reduction with a modal analysis. So it's both a modal and a nodal reduction. It brings in some coordinates here that are generalized coordinates, UQ, and the analysis set is broken into some generalized and some physical coordinates. At the very end, the generalized coordinates become the master one. Let's break down those F set of variables, which I've been calling a free set, and assuming that prior to that you've already taken out multi-point constraints and single-point constraints. So here's your total F set on the left, and on the right here we have the omitted degrees of freedom as before with the Guyan approach, and then we have the generalized coordinates, those that are used for rigid body mode description, and then some free coordinates here and some rigidly restrained coordinates. Some of these are a new concept now. I won't go into details on that. It's a generalized coordinate that is a surviving set though. So those generalized coordinates are the ones that drive the whole problem. Here's the kind of mapping that's developed and progresses from these coordinates on back to these U sub F coordinates over here. There are some approximate modes involved here, And this is related in a sense to the super element approach, where you divide a structure into these segments. This is really an advanced topic, and the mappings are intricate, and I have to admit failure. I wanted to show a simple hand calculation for this method, and I could not do it. There's just too many variables involved, and if you have to start out with 5 or 6 degrees of freedom, by the time you do the mappings to bring it down to the final solution, it's just too complicated for a simple hand calculation. But many people like this implementation in NASTRAN and have gotten used to it for vehicle dynamics. Another reduction method that's popular with some people is the component mode synthesis. This competes nowadays with the Lanczos method, and it's useful for very large problems. It's a superelement concept. It's a dynamic version of superelements or substructuring. And you use those vibration modes of the superelements to infer what the properties of the entire system are. There are at least 2 versions of this kind of approach, and one is where at the joints between the superelements you develop the individual element or the superelement properties with fixed boundaries, and the other method is where you have free boundaries. And this is an advanced topic. Some people prefer the fixed boundaries, even though experimentalists prefer the free boundaries. This may be another one of these areas where, depending on the problem you're doing, you would like to use one approach or the other. Our problem session will concentrate on the Gyan reduction. It's one that we can actually do some hand calculations with. The first problem I take is a 2-element line assembly which is vibrating along its axis. And the idea is to determine the frequency response of this system using this static condensation. I'm going to ask 2 things. I don't want the whole problem solved, but just to find the mapping matrix for the coordinates for either choice of analysis degrees of freedom, namely the motion at the midpoint here or at the right end, and then to explain which of those